Yes. So sorry for the interruption. Okay. So have you solved all the have you solved the previous problem and did you get 31 by 96 W square L by AE? Everyone?
I am getting 19 by 96.
Oh, actually the answer is 31 by 96 W square L by AE. Do you want me to solve the problem?
No, sir. I just want to confirm for prismatic bar due to self weight U is equal to W square L upon 6A.
Yeah, but you can't actually directly add it. Okay. See, for the self weight of a prismatic bar is W square L by 6A. That is correct. Okay. But here, the for the given question, okay, the Pxx you should write it as W by 4, the weight of the flange. Okay, that will be as a pure axial load. Okay, plus W into X by L. And for this whole thing you have to do the squaring. Okay, for example u is equals to integral 0 to L, okay, which is the length of the prismatic bar into pxx square dx divided by 2ae. Okay, so for this pxx you have to write it as w by 4 plus w into x by L the whole square dx divided by 2ae. So if you solve this, you will be getting 31 by 96 W square L by AE. Okay?
Okay, okay, sir. I was directly adding it.
That's what. See, for strain energy alone, you should not do that. Okay? Because we have already seen, right? P1 plus P2, you can't directly add the strain energy of this plus strain energy of this. Okay? Combined P1 plus P2, the whole square should be there.
Okay, means for any condition we should not add.
Yes, for any condition, you should not add like strain energy of 1 plus strain energy of 2, something like that. I mean, strain energy due to load 1 plus strain energy due to load 2, like that, you should not do.
Okay,
That was the thing which we have seen in the first example itself. Like when I showed you, right, P1 separately, P2 separately, then P1 and plus P2 separately. Directly, I could have done, if I could add, I could have written like U3 is equals to U1 plus U2. But we haven't done that because U3 is nothing but P1 plus P2 the whole square. So this additional term due to 2P1 P2 will be there. Similarly, for this case also, it will be there.
okay, sir.
Yeah.
Here flange weight is the pure axial loading.
Which one?
Flange weight.
Yes, flange is pure axial load because here they have asked the strain energy of a prismatic bar only, right? So when you take this prismatic bar, okay, due to this you have self weight W plus you have one axial load which is weight of the flange which is W by 4. Okay,
Okay, sir.
yeah. So now we will proceed to strain energy due to bending moments. Okay. So let's first go for a simpler case. Okay. Like you have a cantilever beam and you have a moment like this, which is M. So if I have to write the strain energy for this kind of loading, what should I write here? Let's say this as the beam as length L. So I have to take the moment at any particular cross section, right? So if I take the moment at any particular cross section, what I will get? Integral 0
Same
to, yeah,
MX
m
dx.
square L by
yeah, m
2
square,
E.
yes, m square L by 2EI, because for this particular cross section when I take the bending moment from the right hand side it will simply be M, right?
G sir.
Yeah, so I can write it as m square into dx divided by 2EI, which will not be nothing but m square L by 2EI. Okay, so can you find out the strain energy for this? W whose length, this beam is of length L. First, you have to find out the bending moment at any particular cross section, and then you have to proceed for strain energy calculation. Okay, that is the procedure. So if
W
I
square L cube by 6 EI.
W square L cube by 6EI, yes, that is the answer. So here I am taking this section XX, okay, and then if I take the right hand side, okay, like this as the length X, okay, with sign I have to write what is MXX here, bending moment at the section XX.
minus W into X.
Yes, minus W into X. So if I write this 0 to L minus W into X the whole square dx divided by 2EI. So if I expand this, I will be getting W square L cube divided by 6EI. If I integrate this, I will get this answer. Okay? Is it fine?
Yes, sir.
Yeah. So let's move on to the next problem. I have a simply supported beam. And I have a load of W which is acting at a distance of L by 4 from one of the ends, and this is 3L by 4. Okay, so for this beam, can you find the strain energy? First of all, what should I do here? What procedure can I follow here?
First of all, find reaction, find
Okay.
equation for M, then evaluate U.
Again, can you say?
Find reaction at A and C,
Yeah.
then moment equation at any cross section at any distance X,
Yes.
U.
Yeah, and then you can find out the strain energy. But for this, first let's find out the reactions. Okay, so what is the reaction at support A?
3W by 4 and W by 4.
Yeah, 3W by 4 in the upward direction, and here it is W by 4. See, the reaction calculations and all, I am not doing it again, okay, because we have seen already. So if anyone wants me to do the reaction calculation also, I will be doing that. Okay, if anyone wants me to do, you just please inform me. Okay, so I am assuming like you have got the reactions value correctly. Okay, so after getting the reactions, so here if I can I write like any single bending moment equation all through the beam? Is it possible?
No, sir.
Yes, sir.
So yes or no?
सर हाँ मतलब टू पार्ट्स में ब्रेक करके.
Yeah, we have to break this beam into two parts because I couldn't able to write within a single bending moment equation all through the beam. Okay, so what I will do is like here I will split the strain energy as strain energy due to part AB plus strain energy due to part BC, so that I could write based on one bending moment equation. Is it fine?
जी सर.
Yeah. So here I am taking for AB section I am taking a cross section, and for BC I am taking a cross section. So this from this I am considering here as X, and from here I am considering here as X. Maybe I can consider from here also X, but the solution becomes complicated because I have to take the left hand side equations. The moments due to left hand side loads into consideration. Whereas if I take X from here, like I could use only one load. Bending moment due to this W by 4. Okay. Understood why I am taking from this side X?
Yes sir.
Yeah. So for AB, like, can you say what is the bending moment equation?
Sir, is the answer 9 by 512?
9 by 512, no. It is 3 by 512.
Please repeat, sir.
3 by 512.
Okay.
Yeah. So for AB, can you find? Can you say what is the moment equation for the part AB?
3W by
Okay.
4.
Hmm.
into x.
Yeah, into x, because left hand side clockwise direction, so it is positive. Okay, into x. This is the bending moment equation into the whole square divided by, I mean, dx divided by 2EA, and the integration is from 0 to L by 4. Okay, plus 0 to 3L by 4, because here I am taking x from this side, so here it will be 0 and this end it will be 3 by 4. Okay, so here what will be the bending moment equation? It should be W by 4 into x, right?
Sir, in the between of the question, can we shift our reference frames also?
Yes, that is possible. See, from here I have, for example, see, we have actually divided this into separate beams, right? Into two parts. Okay, so we can actually shift our references. That's not an issue.
Okay, sir.
Yeah. But altogether, what we need is the strain energy between these two parts, and that doesn't depend on the reference. Reference point which we are choosing.
Sir, is the strain energy per unit volume or strain energy in the full beam, whole beam?
This is actually strain energy per unit volume.
Okay, sir.
Wait. I will confirm. Okay. It should be strain energy. No, this is actually a strain energy for the whole beam, not per unit volume. Okay.
Okay, sir. Okay.
Yeah. This is because we are actually taking L length of the beam into consideration, right? And we are actually taking moment of inertia also. So we are not dividing by any volume. Okay. So this is for the whole beam itself.
Okay.
Yeah. So divided by 2E into I. So can you say what is the answer for this? Here I can write this as 9W square divided by 80, 4 square, right? 4 square is 1632 EI, integration of 0 to L by 4 x square dx, plus this I can write it as W square divided by 32 EI, integration of 0 to 3L by 4 3L by 4 x square dx. So if when you are integrating this, you will be getting u as, I'm writing the final answer here. Okay, 3 by 512 W square L cube divided by EI. Is everyone getting this answer?
Yes.
I could hear only one yes. So others are doing right.
Yes.
Yeah, if you cannot follow anything, you just ask me. Okay. Yeah. So shall we proceed to the next problem?
Yes.
Yeah. So
Yes,
the
sir.
last problem which we are doing in strain energy due to bending moment. Okay. This is uniformly bearing load. Okay. And this length is here. I mean, this load is W, small w. Okay. Small w Newton per meter. So the length is L. Can you find out the strain energy for this? So what is mxx at any particular cross section? Let's imagine, like, say from this side can I choose x, or from this side can I choose x?
So right side वाला अच्छा रहेगा.
Yeah, because here we can easily write the bending moment equation. Okay. So what will be mxx then?
It will be half into W x by L into x by 3.
Yes. And whether it's positive or negative value.
सॉरी सर 2x by 3 होगा अब ये पॉजिटिव नेगेटिव ये नहीं पता सर.
Okay, here positive and negative doesn't matter,
Negative.
but yeah, negative. Because on squaring, yeah, negative will be turning to positive. Okay, but when we are writing the bending moment equation, it should be like in terms of sign. Okay, so if I write the bending moment equation, what is the shear force like W into x by x square by 2L, okay, into x by 3, which is acting at a distance of x by 3 from
नो
here.
सर 2x by 3 पे कर रहे हैं. हाँ
Yeah,
सर सॉरी x
this
by
is
3 पे कर.
yeah, acting at a distance of x by 3. The total shear force here, for example, this is W into x by L, right? This section, I mean at xx, yeah. Oh, sorry, I have written it here.
उधर से 2x by 3 है
Yeah,
इधर
it
से.
should be here. Okay, there the wxx is actually nothing but W into x by L. Okay, and if I want to calculate the bending moment, then I need to find out the total area of this, okay, and then I have to make it to act at its centroid, okay, so as to calculate the bending moments. So therefore if I want to calculate the total area of this, it will be like a triangle, right? So 1 by 2 into wx by L into the distance x, so it will be wx square by 2L, and which is acting at a distance of x by 3 from here, sorry, x by
2x
3,
by
yeah, x by 3 is from here, not here. Okay,
1 by 48.
uh, can you repeat the answer?
1 by 48.
No, it should be 1 by 504.
Oh,
Yeah, so u is integral 0 to L mxx the whole square dx divided by 2ei. Okay, so if I'm integrating it from what is xx here, minus w x cube divided by 6L d whole square into dx divided by 2ei. So if I simplify this, it will become w square. So negative I'm taking to positive, w square divided by 6 square is 3, I mean 36 L square, right? 36 into 2, 72. So 72 L square EI into x cube is x cube the whole square. Okay, so x power 6 dx, 0 to L, integration 0 to L. Okay, after now what I have written is correct?
Yes, sir.
Okay, thank you. So when I integrate this, x power 7 divided by 7, 0 to L. So 72 sevens are, I think it's 504.
04, yes sir.
Yeah, so it will be W L power 5 divided by 504 E I. Is everyone getting this answer?
Yes sir.
Okay. So you are pretty much confident about how to calculate strain energies due to bending moment also, right? And due to various loads. So now shall we proceed to Castigliano's theorem?
Yes sir.
Okay. So 1 minute and take this. Yeah. Castigliano's theorem. This is CAS, okay? So Castigliano's theorem. So this theorem is actually very much useful in unsymmetrical loading for simply supported beams, okay? This is very useful to calculate deflection, okay, in unsymmetrical loading in simply supported beams. The main drawback is like only one load should act. Okay. Here the main drawback is like only we can find out the deflection only when one load is acting. Okay. So we have already seen, right, u is equals to, for a beam it should be integration from a to b mxx the whole square dx divided by 2ei into xx. For example, if e and I are changing across the beam. Okay. So therefore, as per this theorem, okay, as per this theorem, we can find out the slope at any point, or else, like for example, maybe I will write down the whole theorem. Okay, I can find out the slope at point A by partially integrating the strain energy with respect to the bending moment alone. Okay, where ma is the moment acting at point A. Okay, and I can find out the deflection by partially integrating the strain energy with respect to load acting at point A, where WA and MA are the concentrated point load and the concentrated moment. Sorry about my handwriting. Acting at cross section A. Is this fine or not? Okay.
Yes.
Yeah. For example, let's say if I have a beam like this, if I have a cantilever beam like this, and it is loaded at point B by a moment M. Okay. So from this, as per this theorem, what I should do? First, I need to find out the strain energy of this beam, and then I need to partially differentiate the strain energy with respect to M, so that I can get the slope at M. And then if I differentiate the strain energy partially with respect to W, then I can find out the slope, I mean deflection at point B. Okay. Wherever the
Here,
yeah,
sir,
yes.
here is no W.
Here is no W, yeah, but let us see how we can calculate the deflection when there is no W. Okay,
Okay, sir.
yeah, we will do this sum. Okay, so I'm taking
Sir, it
this.
was not a simply supported beam, sir, that you draw.
Yeah, I would say like it is very useful in unsymmetrical loading and simply supported beam. Okay.
But also useful in any type of
Yeah,
beam.
yeah, any type of beam, cantilever beam also it's fine. But only drawback is like there is only one load that is acting.
In
Mhm.
except SSB.
No, no, no. For any type of beam. For any type of beam, there should be only one load that is acting.
Okay, sir.
External load. Okay, not including the reactions. Okay. Maybe after solving some problems, you will get to know. Okay.
Yes.
Yeah. So let's take this problem, and then this is the moment direction I have given. Okay. This is A, B. So can you say what is the strain energy for this? It is m square L by 2EI. Simple, right? Because here it is constant bending moment. So here what can I find out? Only theta B I can find out and YB I can find out. Not the slope and deflection at any other point. Okay? If I want to find out the slope and deflection at any other point, what method should I use?
Deflection wala sir.
Yeah, deflection equation I can go for. Otherwise, moment area method I can use, right?
हाँ sir. Yes
Yeah.
sir.
Okay. So we will find out what is theta b and yb. Okay. So what I should do for finding out theta b, I should partially integrate. I mean differentiate this with respect to m. Yeah. So what will be the answer if I partially differentiate this? 2ml divided by 2ei, which is nothing but ml divided by ei. And the direction you can find out from the direction of this moment. Okay. So which direction it is, clockwise or anti-clockwise?
Anti.
Anti-clockwise, positive.
Yeah, anti-clockwise. Okay.
Yes.
Yeah. So now, how can we find out the deflection? So here, as some one person pointed out, here we don't have any point load, so that we can directly have an equation of strain energy in terms of W, and then if I partially differentiate that strain energy with respect to W, I will get the final answer. But here I am not having the strain energy in terms of W. So what I will do is like I will introduce a dummy force, I mean dummy load. Okay. Say for example,
What?
yeah,
Theta B is sir clockwise sir.
it is anti-clockwise. It should be anti-clockwise. See, for example, this will be something like this, right?
Okay sir. Okay sir.
Correct?
Yeah sir. I thought it will be downward. Okay.
Okay, okay. Yeah. So what I'm doing here is like I'm introducing a dummy concentrated point load in the upward direction. For example, here. Okay, this is a dummy concentrated load I am including here. And after writing the bending moment equation and the strain energy value, I will put the dummy force equals to 0. Okay, so that I will get the actual deflection at point B. That is the procedure I will be following. Is it fine or not? Is it clear or not?
Yes.
To everyone?
Yes, sir.
Yeah. So I'm introducing a dummy load because I don't have any W to differentiate with. Okay. So if I take the section XX, what will be the bending moment equation at section XX then? Let's say this as X.
Due to only the dummy load.
No, no, due to dummy load as well as due to the bending moment.
M plus Wx.
Yeah, it will be M plus Wx. Good. So when I am writing the strain energy equation, it should be integral 0 to L mxx square. I can write it as m plus wx the whole square into dx divided by 2 into e to I. Okay, so I can integrate this after expanding this. Okay, so 1 by 2 e I is, I have taken it outside. Only after the integration you have to put the dummy force equals to 0. Okay, so 1 by 2 e I have taken it outside. Integral 0 to L. If I expand m square plus w square x square plus 2 m w x into dx, which is equals to 1 by 2 ei m square into x. So I will maybe integrate and I will apply that in it. M square x plus w square x is x cubed by 3 plus 2 m w x square by 2, applying from 0 to L. Okay. So when I apply this, it will become m square L divided by 2EI plus W square L cube divided by 6EI plus 2MW x square L square by 4EI. Okay?
Yes, sir.
Yeah. So this is the total strain energy value. So now what should I have to do? I have to partially differentiate this with respect to B. I mean with respect to W. Okay. So if I partially differentiate this with respect to W, what I will get? Anyone? 2WL cube divided by 6EI plus MW, if I partially integrate, to ML square divided by 4EI. Okay? This is the final expression, right?
Yes.
Yeah. So, but here you don't have any W. You just introduced so that you can actually partially differentiate. So what I will do is, like, at the last, after finding out the after partially integrating, I mean after partially differentiating, I will put this W equals to 0 to find out the actual YB, or the actual deflection at point B. So it will be ML square by 2EI. Is this fine?
Yes.
Yes, sir.
Yeah.
Yes, sir.
No doubts, right?
After a partial integration, then only we.
Partial differentiation, then only we have to put W equals to 0.
Okay, okay, sir.
Okay? Yeah.
Okay.
So I am proceeding to the next problem on Castigliano's theorem. This is a overhanging beam, okay?
Sir, can you show the previous slide, sir?
Yes.
Okay, sir.
Yeah. Okay, this total length is L, and this is point A, point B. Sorry.
Sir, in the previous question,
Yeah.
if I had to find out the deflection at any point except B, can I
Then,
apply force
yeah.
at that point?
No, actually, in Castigliano's theorem, the main issue is like wherever the load is acting, only at that point I can find out the deflection or the slope.
So, sir,
Hmm.
the point that I am willing to find out the deflection, at that point, can I apply the dummy load and find the deflection at that point?
Yes, that's the thing we have done here, right? See, here what I need is like I need to find out the slope and deflection at point B, because at this point only this concentrated moment is acting. Okay,
Okay, sir.
so
This is
here
clear.
only, so for that only I have introduced the dummy force only at this point, not at any other point on this B.
Okay.
Yeah. So this length is L by 4. So can you find out what will be the deflection at point A? What is deflection at point A? First, what you have to do for this kind of problem?
Reaction.
Yeah. So find out the reactions and find out what is the deflection at point A. I will come within 2 minutes, okay? Yeah. Just for 2 minutes, okay?
Okay.
Yes, sir.
Yeah, have you solved? Has anyone solved?
No, sir.
Reactions finally.
Okay.
Reactions are 5 by 4 W and W by 4 downward.
Yeah. So the reaction at here is 5W by 4, and here it is downwards W by 4.
Sir, I am getting 3W by 4.
Oh, okay.
Yes, sir. 3W by 4.
1 minute. Yeah, we will solve. Okay. So what we will do is like we can take summation. I mean moment about b is equals to 0, right?
Yes, sir.
Yeah. So if I take moment about b is equals to 0, then what I will get w into L by 4, which is equals to, let's assume, see, this causes a moment in this direction. So this side it should cause a moment in this direction. Okay. So I am taking the reaction to be in this way. Okay. So which will be RC into L. Okay. So RC will be W by 4 in the downward direction. So when I take the total, the net force, which will be W plus W by 4, which should be equal to RB, which is in the upward direction. So it will be 5W by 4. Is it fine?
Yes, sir.
Yeah. Then after finding out the reactions, what should I do?
Find
Moment
U.
equation for
Yeah,
2 parts.
yeah, two parts. So I will take U equals to UAB plus UBC. So which is nothing but if I take the bending moment equation at, say, at from here x, okay, so it will be minus W into x since it is left anti-clockwise. Yeah, so it should be 0 to L by 4 minus W into x, the whole square, dx divided by 2ei plus integral 0 to L. So here, which from which side I can take x?
From the C side.
Yeah, from the C side. So it will be right clockwise. So again, it is negative. Okay. So here negative doesn't matter, but still, like for bending moment equation, I'm writing it. W by 4 into x dx divided by 2ei. So what is the final expression you are getting after integrating?
5 by 384.
5 by 384. Yeah. So is everyone getting, or should I have to do the integration?
We will do, sir.
Okay. So 5 by 384 W square L cube divided by L.
5 by 190.
Yeah.
Is the answer 5 by 192?
Yes. 5 by 192.
Sir, is
So
there another way by which we can solve it?
yeah, you can go for moment area method. Moment area method, I think you can go, right? Mm,
Yes, sir. Yes, sir.
yeah, moment area method. By using moment area method, you can find out what is the deflection at point A. Okay.
Okay, sir. Thank you.
Yeah. So if I want to find out what is the deflection, then I need to differentiate with respect to W at point A. So it should be 5 by 384 into 2W L cube divided by EI. So it will be 5 by 192 W L cube divided by EI. Okay. Shall we proceed to the next problem?
Yes, sir.
Sir, reaction at RC direction.
Direction is downward direction only. Why is there any confusion with respect to this RC direction? Yeah?
Okay, sir.
Okay. Shall we proceed to the next problem?
Yes, sir.
Okay. I'm assuming everyone has done this, okay? Yeah. So, again, the second last problem, okay? This is A, and here the spring is attached. This is point B. This is length L. So, again, determine what is deflection at point A. Okay? So, what is the first thing here? Again, to determine the reactions, okay?
Yes.
Yeah. So, what will be the reaction at point B and what will be the spring force?
KX.
Yeah, spring force will be Kx, but actually we need to find out the spring force and then we can find out what is the strain energy which is stored in the spring. Okay. So first we need to find out the spring force by taking this beam alone. Okay.
It will be W by 2, sir.
Yeah, it should be W by 2. And the direction is
Downward.
downward.
Sir, is there any trick to get this quickly?
Yeah, trick is actually see when they have given this kind of simply supported beam or overhanging beam. Okay, the first thing you can do is like find out the summation MB equals to 0. By putting summation MB equals to 0, directly you can find out what is the reaction at point this point. Let's say C.
Yes.
Yeah, for example, this is producing a moment in this direction, W into L by 2. So you need an opposite moment here. So only if the load is acting in the downward direction, then you will have a load in this direction, okay? So, and the magnitude should be W into L by 2, which is equals to RC into L. So it is nothing but RC equals to W by 2.
Sir, here in internal energy calculation,
Hmm.
sorry, U calculation,
Yeah.
we have to include the effect of the strain energy stored in this spring also.
Yes, yes, yes. Because the here you are having the beam reaction only, right, which is acting on the spring. For example, if I isolate the beam, right, you will be having a force which is equal and opposite, which is acting on the beam W by 2, which is exerted by the spring. Correct?
Sir, not able to get, sir. Please repeat.
Okay. See, for example, this is the free body diagram of the beam, right? For example, you have find out this. See, W by 2 is the force exerted on the spring. Okay, whereas an equal and opposite force is exerted on the beam also, which is equals to W by 2.
Sir, beam पर तो downward है ना?
Yeah, see,
Yes, sir.
And you have put upward.
no, from the beam, you are having a force which is acting on the spring.
Okay, sir. Okay.
Okay,
Yes.
yeah. So if, for example, okay, 1 minute. The spring,
Sir, downward, sir.
yeah, the spring elongates here, right? Here, actually, what happens is like the spring elongates. Since you are having a load here in the downward direction, the spring elongates. So, in the downward direction, you will be having a load for the
Yes, sir. It
beam.
will it will
Yeah,
be pulling.
it will be pulling downwards. Okay, now it is clear, right?
Yes, sir.
Yeah, so an equal and opposite force will be acting on the spring also. So for the beam it will be pulling downwards, W by 2. So can you find out what is the reaction at point B then? It will
That
be
W
3W by 2 up.
same.
Yeah. So when you are calculating the strain energy of this entire system, then you have to calculate the strain energy of the spring also, because it is pulling downwards. It is pulling the beam in the downward direction. So you have to take the strain energy of stored in the spring into consideration as well. Okay.
sir only linear addition, na?
Yes, only linear addition. Yeah. Because you see, why you are doing only linear addition? Because you are actually splitting the entire beam into three different parts. One is due to the spring, and another one due to part BC, and another one due to part AB.
Okay, sir.
Yeah, so that only I am doing linear addition. Otherwise, I won't do linear addition. Okay.
Yes.
Yeah. So the total strain energy of the system is UAB plus UBC plus U of spring. So when what, for example, what is UAB? 0 to L by 2 minus left anti-clockwise, yeah, minus W into x the whole square dx divided by 2 EI, and this is again right clockwise. From here I am taking x. Okay.
1/48.
Huh?
First part UAB
Yeah, first part will be
1/48.
okay. Okay. So here 0 to L minus w into x minus w by 2 into x the whole square dx divided by 2ei plus what is the strain energy of the spring?
W by 2 into L theta. Array 9.
Hmm.
Yeah, x square.
Yeah, half k into x, right? I mean half k x square, which means like 1 by 2 into load into delta. The strain energy of the spring is half k x square. I can rewrite this as half k x into x, which is equals to half into force into the deflection.
Yes.
Yeah. So here also I am writing this as half into, here R is nothing but W by 2, right? The load F W by 2 into delta. Delta I can write it as again W by K, which is the stiffness of the spring. Okay?
W by 2K, sir.
Yeah, W by 2K. Yes. Load divided by the stiffness. Okay? We have written everything correctly, right? Half into W by 2 into W by 2K. Yes. So when we integrate this minus W, I mean,
Sir, I have not
yeah.
got how spring energy we got.
Okay. See, the spring energy is nothing but half K x square. Okay, that is the formula which we have learned in our
Yes, yes,
yes, right? So I can split this into half kx into x, correct?
yes.
X square I have split it into x into x. So this kx term is nothing but the force, spring force.
W by 2.
Yeah, W by 2. So I am writing this as spring force F into the deflection in, I am writing it as delta. This delta is nothing but F by K, which is the force divided by the stiffness.
Yes, sir, yes.
Okay, so it will become something like 1 by 2 into F square by K. So here F is W by 2. Understood now?
Yes, sir.
Okay. So here W square by 2EI x square by 2. So if I write x square by 2, it will be L by 2 x square by 2. So if I do any mistake, you just say inform me, okay? X square
By
by 2.
3, sir.
Yeah, what?
X
Oh,
cube by
x
3.
cube by 3. Yeah, yeah. Thank you. Yes. And here if I write this w square by 4 8 ei, here also it will be x cube by 3, right? So it will be L cube divided by 3 plus w square divided by 8k. So here if I have this
1 by 16.
1 by 16, sure?
Yeah, sir.
Okay. W square by 2 ei plus here w cube L cube, w square L cube by 24 ei.
No, sir. 1 by 16 was both sum of both UAB and UBC.
40 80 sir.
Okay.
First term.
So you are saying like the sum of both first and second term will be
1 by 16.
okay. But I'm thinking about this k value. R square by 2k. Thirteen by okay. I think how they have replaced this k with ei, I don't know.
Sir, is there any relation that deflection at point A is going to be twice the deflection at point C?
No, 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 not like that.
Means C will come twice.
No, no, no. We can't be very sure about that.
Yes, sir. Means beam may bend in between.
Yes, yes. No, beam might not bend in between, but I'm not saying like it will be twice of that. Okay?
So, sir,
Okay.
what is the answer, sir? Final answer?
Yeah, actually, I'm looking into that. Actually, I couldn't able to replace this K because here what have the answer as 13 by 192 W square L cube divided by EI.
Okay.
Okay? So I'm trying to find out how I got to this. Because we are having k, right? So
So, sir,
but in the final expression we don't have any k, so how it is possible?
sir, according to me, we can this do this by calculating YC. Then YC is calculated.
Hmm.
That means that K equal to W by 2 YC.
K equal to w by 2 into yc.
Which
Okay.
can be used, sir. I
No,
think.
but that is also not possible. Hmm.
Sir,
Okay.
but K is the property of spring, so
Yes, k is
it
a
has to
proper.
be there.
It has to be there, right? Maybe I think here I missed out the relation between k and ei. I think there should be some relation between k like is equals to 3 times ei or something like that. So that we can actually group this all these terms into a single expression in terms of ei. That does
Means
that make
means
sense?
stiffness of spring might be related with the
Yes,
stiffness of beam.
yes, difference of beam in terms of ei. So if that is possible, only then I could write in terms of this final expression as ei.
Yes, sir.
Yeah, correct, right?
Yes, sir. Both are
Yes.
properties of my
Yes.
properties.
Actually, we have seen a similar kind of problem in the deflection also. So Here I didn't haven't thought of this. Okay. Okay, here let's imagine like k is equals to some x times ei. Okay. So the final expression what you will be getting after applying this will be 13 by 192 into w square by l cube. I mean w square l cube by ei. Okay. So let's proceed like this. So if I want the deflection at point A, it should be dou u by dou w a. So partially differentiating, you will be getting 32 by 96 WL cube divided by EI. Okay, and the direction is downwards. In the next class, I will say what is this expression. Please remind me, okay? Maybe I have to solve this again and then I have to find out what is the value of K I am getting. Okay,
Okay.
now?
Yes.
Yeah. So, shall we proceed to the next problem then?
Yes, sir.
Everyone? Yeah. So this is the last problem which we are doing in Castigliano's theorem. What is the time now? 8:28. Okay. After that, we have to see torsion in shafts. Imagine this is a semicircle. Okay. Imagine this is a semicircle. I mean, a quarter of a circle. Okay. And this is, let's say, its center O. Okay. And here I am having a load W. So I want you to find out what is the deflection at point A, which is applied here. Okay. Do you wish to try or
सर ट्राई कर रहे हैं.
yeah? So first of all, you need to find out strain energy. So for finding out strain energy, you need to find out what is the bending equation at any particular section XX. Okay. Along the length of the beam. So first bending moment at section XX you have to find out. Yes, this. So as anyone trying to find out or any method you have thought of?
By taking small element dx.
Yes. So here I am taking a small element dx. This is very small element. Okay. Here I have given exaggerated one at a distance of x. So what will be the bending moment here?
Sir, I think we
W
can.
into
Yeah.
Sir, I think we can find m with relation to r and sine theta.
Yes.
Then
Yes. Yes.
finding relation between x and x and r sine theta. Then dx
Mhm.
equal to r cos theta d theta, and employing that in the above equation.
Yes. 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 Yeah. So by the same method you can do. Good. So here mxx will, I mean, bending moment at section xx will be minus w into x. Okay. So if I want to find out the value of x here, how can I find out here? This is
r
r.
sine theta.
Yeah, r sine theta. This is theta. So it will be minus w into r sine theta. Okay.
Sir, we
And
can
then
take means the theta from downwards, no problem.
what?
Means from theta on downward side also. Then it will be r cos theta.
Theta downward. Oh, okay. See, if you are saying like I'm taking this as the theta like that.
Yes.
Yeah,
Yes.
that is also fine. But here I want this thing, right? This length I want. So I'm taking theta here, and if I write this, it will be 90 minus theta. So if I take the theta here, then I can write this as 90 minus theta. That is also fine.
Okay.
Yeah. So here I'm taking this as theta. Okay. And then like minus w into r sine theta, and then dx. How can I write dx in terms of r into theta?
R sin theta.
No, dx.
Dx will be r cos theta d theta.
R d theta.
Yeah, it should be r into d theta. Okay, because this is the small elemental strip, so it should be r into d theta.
Sir, x will be r sin theta.
X will be r sin theta. Yes.
It can be written as dx equal to r cos theta d theta. What is the
No,
fault?
no. That is the see. That is the differentiation you are doing. But here, what I am doing is like I have to convert this elemental strip. I mean I have to find out the length of this elemental strip, dx. Whereas x is the distance from here.
Sir, but in the equation,
Hmm. See, in
सर
the
ये जो आपका r थीटा है, ये तो कर्व्ड पोजीशन में है ना, मतलब कि फीलिंग कैसे?
no. See, for example, the x distance is from the right hand side. Okay. Whereas this dx is the length of this small elemental ring.
Sir, I want to ask that
Hmm.
what is the fault in taking
Hmm.
dx equal to r cos theta d theta?
Yeah, actually, like that you can't take because here x is the length of this string. So if I take dx, na, it is something like which I am differentiating this r sine theta, or like which I am differentiating this distance value. So that is not required for this problem, right? Whereas I need to find out what is the length of this small elemental strip or elemental ring. So it should be like the radius multiply this small d theta. So then I can actually convert the integration in terms of theta.
Sir, but what is the
Hmm.
fault in that?
What is the fault in that? That's what, like I'm saying, right? For example, if I what you are saying is like, sir, I'm writing x is equals to r into sine theta, so why not I differentiate this x like that only, you are saying, right, in terms of d theta, and then
Yes, sir.
getting what is dx. But I don't think we can do like this. Because why? Because like I'm differentiating with this distance in terms of d theta. But what I require here is like I want the elemental strip, the length of this elemental strip dx. That I can find out only through this geometric interpretation, not through this differentiation.
Okay, sir. Okay, sir.
Okay, to my knowledge, I'd say maybe you would have different opinion. I think so. Okay,
Okay, sir. Okay.
yeah. So dx we have find out r into d theta. So here theta varies from here to here. So it varies from 0 to how much?
Pi by 2.
Yeah, pi by 2. So here what I will do the integration from 0 to pi by 2 m square, which is w into r sine theta the whole square into dx, which is r d theta divided by 2ei. Okay. So can you say what is the final answer for this? Mm, minus w square. I mean, yes, w square by 2e. I am taking it outside. R is also constant, so r cube I am taking it outside. So what I am left with is sine square theta d theta. So what is integration of sine square theta d theta? Sine square theta I can rewrite it as 1 minus cos 2
Cost.
theta by 2. Correct? Into d theta. Integrate it from 0 to pi by 2. So w square r cube divided by 2 ei into, if I integrate this,
Pi by 4, sir.
yeah, pi by 4.
Pi by 8.
Yeah, it should be pi by 8 into w square r cube divided by ei. So this is the strain energy value. Okay? Has everyone understood?
Yes.
Okay.
Yes, sir.
So when I want to calculate the deflection at point A, then I have to partially differentiate with respect to W. So it will be pi by 4 W R cube divided by EI. Okay? Understood now?
Yes, sir.
Yeah. So shall we proceed to torsion of shafts then?
1 minute, sir.
Yeah. And I want to see, actually they have said like the next week would be our last class. So what you want me to teach in the next week, you please decide and you tell me at the end of the class, okay? Because still like principal stresses are remaining, and I think Yasdeep has covered at the start of the class principal stresses.
Yes, sir. More circle and principal stress was.
Yeah, covered, right? So what
Yeah.
I'm planning is like I won't touch upon those topics. What I'm thinking is like directly I will go to, because torsion of shafts today I can't complete. Only 20 minutes is remaining. So maybe in the last class, which is next Monday, I will be touching a small part on like torsion of shafts, and then I will complete cylinders, spheres, thin cylinders, spheres, and columns. Okay, is it fine
Yes, sir.
to everyone?
Yes, sir.
Sir.
Okay. Since ESDP has covered principal stresses, I assume like you know something about principal stresses. Okay.
Yes, sir.
Yeah.
Sir,
Yes.
here I took theta from downside, and
Okay.
then I wrote that in terms of r cos theta square something, and
Mm-hmm.
I end up with this the same u but in minus.
Same U but in minus.
Yes, because I integrated it from theta equal to pi by 2 to 0.
Oh, but why not like 0 to pi by 2? If you integrate, can you check what is the answer?
Sir, then dx will be minus r d theta.
Dx will be minus r d theta. Oh. How come you are saying that? Is there any specific reason you are saying like dx is equals to minus r d theta?
Uh, because since the
Hmm.
x direction is positive from left to right, sorry, right to left, but we are up
Huh.
left to right, so it will be negative, sir.
Yeah, yeah. Makes sense.
Can you repeat once, sir?
Yeah, actually, yeah. Can you repeat it once?
Since x is positive from right to left, but by considering theta from the bottom line, then you are approaching from मतलब d theta जो है उसकी तरफ मूव कर रहा है ना clockwise, तो dx's will be in the मतलब right direction.
See, what he's saying is like, for example, I mean, sorry, this is dx, right?
Yes.
Yeah, so this is r, and this is here what we have assumed is like d theta is in this direction, because we have taken x from this direction. Okay, but when you take theta from this, okay, what you want to do is like, since dx is taken from, I mean, since x is taken from this right hand side, so if you are taking d theta in this direction, then it should be minus into r d theta, because you are going from this direction.
Okay, means theta is approaching from one side and
Yes,
we
x
are
is
taking
coming
x
from
from.
other side.
Okay.
Okay, so maybe you can try with this and you can check the answer also. Okay.
Yes, sir. Then it will going to use same results.
Okay. Okay. Thank you. So shall we proceed to twisting moment? I mean, torsion of shafts then.
Yes.
Yeah.
Yes, sir. So thank you for this topic, sir.
Fine, fine, fine. Okay. So coming to the torsion of shafts. Torsion, I am moving a bit faster. Okay. I'll just say what is required so that like it would be sufficient. Okay. I'm not going to get into how those formulas came and everything. So this means like one end of the shaft is fixed. Okay, the left end is fixed, whereas the right end is free. Okay, and you are applying a load like this, an equal and opposite load. Okay, due to this, what happens? There is a twisting moment which is developed at this free end of this cross section. Okay, so the same thing. For example, let us imagine this to be diameter d. Okay, so what will be the twisting moment then? Till now we have seen about bending moment. So we have already seen, right, what is the difference between bending moment and twisting moment?
Yes, sir.
Yeah, what is twisting moment which we have seen? If the moment plane of moment is parallel to the cross section, then it is twisting moment. Whereas if it is perpendicular to the cross section, then it is bending moment. Something like that, right?
Yes, sir. Yes, sir.
Yeah.
So twisting moment will be PD.
PD. Yeah. Okay. And what is the sign convention which we have seen? For example, if I take this as the circular bar, what is the sign convention which I have? I think I have told you this.
The right hand rule.
Yeah, right hand rule. So when you apply here the right hand rule, it is pointing towards the cross section, right?
Yes, sir.
Yeah. So for twisting, I am using an arrow, a double-headed arrow. Okay, and an equal and opposite reaction would be developed at this end because it is fixed, and this is T, which is equals to P into D. And what is the sign convention? I mean, okay, for finding out the direction, we are actually using right hand rule. Whereas for sign convention, whether this twisting moment is positive or negative, for that, what we can use? Like I have told you this also. Pointing away from the cross section is taken as
Negative.
negative. Yeah, pointing towards the cross section is taken as positive. So here, this is a positive twisting moment. So if I draw the twisting moment diagram, it will be positive. I think we have seen all these things in deflection. I mean, before SFD, huh? Like with respect to like
Free
small,
body diagram.
yeah, free body diagram we have seen. Yeah, this P into D. Okay. So when you are actually having this kind of a torsion, what happens is like when we take this free end, okay, when we take the cross section of this free end, okay, this free end actually due to this twisting moment, what happens is like it experiences a torsional shear stresses. Okay, for example, if I want to draw the variation of this torsional shear stresses, it will look something like this. Yeah. Where the torsional shear stresses are maximum at the outer fiber or the periphery of the cross section. whereas it is 0 at the centroid. Okay, you can intuitively imagine, right? Like for example, when I'm twisting what to say solid rubber, okay, while holding the one end of the rubber, and if I am twisting it at the center, you can't a small twist I am giving, not a big twist, okay, a small twist I am giving, and you can see at the center there is no deviation with respect to its shape, whereas at the periphery of the free end, like, it will suffer the maximum distortion. Okay, so based on that, we are actually intuitively saying like it is 0 at the center, and whereas it is maximum at the periphery. Okay.
Sir, if in case
Yeah.
the torsion is not applied on the periphery, it is applied like not at distance d, which is the diameter. it एक center पे apply किया है, एक नीचे किया है.
Okay, okay, but still it is acting onto the entire cross section, right? For example, what you are saying is like, sir, I am not applying a load here, whereas I am applying a load here.
Yes,
This
sir.
is the, yeah. This also ultimately contributes to a twisting moment to the entire cross section whose magnitude is less than PD. That's it.
So, sir, it has no relation with like that at center. What will be the shear stress?
No, at center the shear stress always remains 0 until and unless you have a direct shear.
Okay, sir.
Okay, due to twisting moment, the shear stress at the center is 0
means
because,
means we
yeah,
are assuming rigid cross section.
we are assuming what cross section?
Rigid.
No, no, no. This cross section is deformable only. We are assuming this cross section to be deformable, but at the center point, if you are giving a small twist, or if you are giving a small twisting moment, you will see the center point will always remain at the same position. Okay, it does not it does not get distorted from its original position, whereas all the extreme fibers, or for example, as the distance of the fiber, or the distance of the point from the center increases, you will find more distortion. That's the point which I'm trying to make here.
Yes.
Okay, so what can I say here is like the shear stresses is directly proportional to the radius.
Okay, sir.
Okay, for this only I'm for trying to prove this, I have said this.
Sir, if only one P is applied, that is on the periphery,
Okay, then
then sir, same
then what will,
magnitude.
yeah, then what will happen on the periphery if you are applying means, then it will act as a like a bending or a shear load, right?
Yes, sir.
So you won't be having any twisting moment then.
I
But
think we will have,
sir,
sir, because we will shift it to center.
Mm, no, for example, see what one person has asked is like, you are having a cross section like this, okay, okay, and you are giving a load like this. That is the thing you asked, right?
yes, sir.
Yeah, so if you are giving a load like this, then if you are actually changing it to this point, then an equal and opposite force, okay, pp, and due to this p into e, mm, this distance will be d by 2.
So,
Yeah, and then you will be having a moment. Yes, as another one person stated, like you will be having a twisting moment as well as a direct shear load, or a direct shear load on this particular cross section you will be having.
okay, sir.
Okay, twisting moment combined with shear load.
Okay, sir. Thank you.
Yeah, as someone pointed out, this is true. Okay.
Yes.
So, but here what we are actually speaking is like pure pure torsion, like there is no direct shear load which is applied on the particular cross section. Okay, that is in this chapter, that is the basic assumption which we are making here. There are no direct shear loads which are actually acting. Only due to torsion there are shear stresses which is developed. Okay, during that point you will
Yes.
be having, yeah, tau shear stress is directly proportional to the radius, or the distance of the fiber which is away from the centroid. Okay.
Okay, sir.
Sir,
Yeah.
for this case, if the left half hand is fixed, what is the reaction at the bottom of the left hand?
Can you please repeat your question?
For this case, both bending and axial loading,
No,
if the
no,
left
no,
hand is fixed,
no. For this case, you have only like for example, yeah, you have bending also. You have bending also because this is fixed at this point.
what is the reaction at that fixed bottom point?
Yeah, fixed bottom point. You will be having one shear reaction also. Okay, which is P, as well as you will be having P into this total length. Yeah, let's imagine this total length as L. So equal to that, you will be having a reaction P into L, moment reaction. And as well as due to this twisting moment P into D by 2, you will be having a twisting moment reaction which is equals to P into D by 2.
Okay, sir.
Okay? Does it make sense what I am saying?
Yes, sir.
Yeah. So directly I'm going to write here one equation which is very important for torsional shafts. T by J equals to tau max divided by capital R, which is equals to G theta divided by L. This is applicable for a pure prismatic bar, okay, a circular bar which is subjected to a torsion T, okay, or a twisting couple. Here we can say T as torque or twisting couple, anything, okay. And what is J here? It is polar moment of inertia, okay, which is nothing but, for a circular shaft it is nothing but Ixx plus Iyy, or for any member it is polar moment is nothing but Ixx plus Iyy. What is the value for J for a circular shaft?
Pi by 32 D.
5 by 32.
Yeah, pi by 32 d power 4. And what is G here? Shear modulus of the material, okay. And here L is length of the shaft, and tau max is the maximum shear stress. And what is theta here?
Angle of the twist.
Yeah, angle of twist at the free end, okay. Theta
Radius.
is, yeah, theta is angle of twist at the free end. Can I extend today's class up to 9:15? No issue, right?
Okay, sir.
Yeah.
Okay, sir.
Yeah. So theta is angle of twist at the free end. Okay. So if I want to see physically what is the angle of twist, so I'm taking this same cross section, this what to say, this circular cross section, when I'm viewing it from this side, right side. Okay. And if I take this up, like say this twist, I am saying this as angle of twist at the free end. Okay, theta.
Yes, sir.
Is it fine?
Yes, sir.
Yeah. For example, initially there is no twist. Okay. Initially, for example, if I take any fiber, let's say this is the center. Okay. The only the upper half I am taking. Okay. Let's say this as the center point O. Initially when I am not applying any torque, it is let us imagine a fiber, okay, or what, let us assume, let's take a small line for, imagine like you have drawn a small line here, okay, and after the torque is applied, this line is shifted to something like this. So this twist angle is known as theta. You can visualize it, right?
Yes, sir.
Yeah.
Hmm.
And can you say where this angle of twist will be zero along the length of this?
At
Uh,
the
yeah.
left hands fixed.
What? Fixed end. Yeah. At the fixed end, you will be having theta equals to zero. Whereas at the free end, you will be having theta is equals to, say, for example, a value, let's say A. Okay. Or let's say theta also. So at the free end, you will be having theta equals to 0, whereas at the fixed end, you will be having the maximum angle of twist theta max. Okay. So what from this, what can we infer is like theta is directly proportional to the length of the shaft. Okay.
Yes, sir.
Agree.
Yes, sir.
Yeah. So theta is directly proportional to the length of the shaft. Then the second thing what I want to make here is like, again, as we have already seen, the for example here you are having a zero shear stress, okay, whereas the shear stress is maximum at the outer periphery of the shaft. Similarly, you will be having shear strain, okay. So in which uh, direction or in which side I can actually view this shear strain? For example, maybe I will draw it legibly, okay. Let us take this as the center point, okay, and this is a single line and this is another single line, okay, and this is the line joining the centroids of each cross section, and here I am having the fixed point, okay, and here I am having this section like this. So this is the line joining the initial, this is the initial thing, okay. Like this, I'm having a initial what to say, a line which is drawn on the cross section, okay. After twisting, what happens, this line is twisted to some degree theta, which I can see from right hand side. When I view this from the right hand side, this is the upper half only I'm showing. Similar to that, you are having a downward half here, okay, that I am not drawing, only the upper half I am showing, and this is the fixed end, okay. So after twist, what happens, it goes here. So this is the deformed shape, okay. From here, if I draw a line like this, okay, so this is known as the shear angle phi, okay. This shear angle phi is maximum at the, again, out at the outer periphery, whereas if I take for example the shear angle here, it is a very less value which is directly proportional to the radius.
Sir, here shear angle is measured with means.
From the top side, for example, when you are viewing from the top the entire cross section, I mean the entire length, this is the total length L, okay. From this side if I see, I could see this angle of twist, whereas from the top side if I see, this is the total deformed shape, and this is the original shape, and this is the final deformed shape. And when I join this original shape with the final deformed shape to this fixed end, okay, I could see the maximum value of phi at the outer periphery, whereas this maximum value of phi will actually decrease, and at here it will become 0, okay. For example, let's imagine like at this radius, let's say this r equals to capital R, and here let's say this r equals to small r. Okay, so if I draw here, what happens is like I'm not see due to my poor drawing, maybe I think you couldn't able to figure it out.
Sir, means that top horizontal line is inclined one.
Yes, this top horizontal thing is actually not a straight line, it's actually an inclined line. For example, when you are viewing from the top now, it will be something like this, and this angle I'm saying it as phi.
And it is shear,
Yeah,
shear.
shear strain, yeah, and this will be something like this. And when you are viewing it from the right side, you will look something like this, and
Various
this angle
theta.
is theta. Yeah, now you can imagine, right? This is, yeah, right side, and this is top side. Fine.
Yes,
Yes.
sir.
Yeah, this and this shear angle actually reduces when I'm moving it towards the center. That's the point I want to make. This shear angle actually reduces. Here I'm making it at phi dash, and it will be 0 at the centroid. Okay, understood now?
Yes, sir.
Yeah, if you have still have any doubts, like you can take a small like what to say, a cork like thing, and then you can twist by holding one end, and then you can see, okay, at the top like you will be having the maximum shear strain, whereas like you can't cut any sections, but you can actually intuitively imagine like at the center you won't be having any shear strain. Okay, so only we are getting like both the shear strain as well as the tau is actually 0 at the centroid at r equals to 0. Okay.
Yes, sir.
Yeah. So what we have seen is like this equation we have seen, and how phi varies with radius, how theta varies with the length, and how shear stresses varies with the radius. All these three things we have seen. Okay. Now what we shall do is like we can, I think we are in good position to solve some problem. Okay. So before proceeding to solve problems, let's take this equation: T by J equals to tau by R max, I mean R, which is the radius of the circular shaft, which is equals to G theta by L. Okay. So when I take this, let's these two equations, T equals to, I mean tau max, or let's say tau max. Okay, tau max equals to tr by j. Okay, then I can write t by j divided by r. What can you say about this j divided by r term?
Polar section only.
Yeah, polar section modulus. Okay, which I am naming here as zp. Okay, and other than that, what can I say is like tau, since tau is directly proportional to the radius, I can write for example, if I know the tau max at, say for example, at any radius r, I mean at the outer radius r, then I can find out tau at any radius by using what? Tau by tau max equals to directly proportional, right? So r divided by r. Okay, this relation is extremely useful, and also I can write theta dash is directly proportional to L, so I can write it as theta dash is equals theta dash divided by theta, where theta is the angle of twist at the free end. Okay, which is equals to, where theta dash is the angle of twist at any length, which is equal to L by capital L. Okay, and the torsional stiffness can be given by k equals to, what is stiffness actually? Load divided by the deflection. Here the deflection is angle of twist. Okay, so you need t by theta here. Okay, so it will be gj by L. So this is known as This Gj by L is known as torsional stiffness. And what is torsional rigidity here?
GJ, sir.
Yeah, Gj is known as torsional rigidity. Okay, so all the basics clear?
Yes, sir.
Yes,
Yeah.
sir.
So here we will try to solve one or two problems. Okay. Yeah. So here they have given the cross section of a shaft at the free end. Okay, maybe the time is 9:08. So we can take this as the last sum. Okay. And in the next class, we will see about shaft in series, shaft in parallel, and statically indeterminate shaft, and then theory of thin cylinders, spheres, and columns, and then we will wind up. Okay. So the coming to this problem, the cross section of a shaft at the free end is shown. Determine the following if maximum shear stress developed is 100 megapascal due to twisting moment. So you have to find out the torsional shear stresses at different points as shown here, like A, B, C. So can you say what is the torsional shear stress at point A?
100 MPa.
100 MPa. Yeah. Why? Because it is at the outer radius. And what is the shear stress at point C also? It is also 100 MPa. And what is how you can find out what is the shear stress at point B?
Tau by tau max equal to R by
Yes. Yes, tau by tau max equals to here tau B, let's say tau B by tau max equals to RB by R max, which is actually nothing but the radius. Okay, so tau B divided by tau max is 100 megapascal, which is equals to RB. What is the value of RB here? This is 30. Okay, this is 30. So 30 divided by capital R is 50. So what is the value of tau B?
60.
0.6.
Yeah, 16 megapascal. Okay, so the first part is done. What is the second part? Shear angles at different points as shown. So what? How can you find out phi? Shear angle phi.
R theta equal to phi into L.
Okay, for that I need to know about theta also, right?
Yes, sir.
So is there any other way? Shear stress is directly proportional to shear strain, so shear stress is equals to G into shear angle phi. Correct?
Yes, sir.
Yeah, so here G value they have given, shear modulus they have given, so directly I can apply this and I can find out what is phi A, or like I can find out what is phi C also. Like phi A equals to phi C here, okay? So 100 megapascal equals to 80 gigapascal, so 80 into 10 to the power of 3 into phi A. So from this I can find out what is the value of phi A. What is the value of phi A? Radians, okay, which is equals to phi c, or we can say which is equals to phi max also. So from this, what how you can calculate what is the value of phi b? Anyone? Again, what we have discussed, phi is directly proportional to r, right? Yes or no?
Yes.
Yeah, so phi b by phi max, which is equals to 30 divided by 50. So from this I can find out what is the value of phi b. And phi b here it is 7.5 into 10 to the power of minus 4 radians. I'm assuming everyone is following, okay? If you have any doubts, you can please ask.
No, no.
Yeah.
Sir, we can proceed to this problem with more circle as well, na sir?
Most circle. How?
Like maximum shear stress, calculating by maximum shear stress problem.
See, only using most circle, I can only find out what is the maximum shear stress and also what is the shear stress at any orientation. Okay, I cannot find out what is the shear stress at any point.
Hmm.
Okay, so here I don't think most circle will be useful.
Got it.
Yeah. So what will be the theta value? So the second part is also done here. So what is the angle of twist at different points for this cross section? Whether it will be same or whether it will be different for all the points. What is this cross section actually? Whether it is at the free end or the fixed end? At the free end, right?
Yes, sir.
Yeah. So what will be the angle of twist at point A, point B, and point C? Whether it will be same or different.
Not would be same. That might be different.
Oh. See, actually, what we have discussed in our previous theory part, like theta actually varies with the length. Okay, and for a given length, for a given cross section, theta value is same.
Huh.
Okay, so coming to this is for a given cross section. So theta value should be same, right?
Yes, sir.
Yeah. So I'm going to the next slide. Okay. Okay. I'm solving it here. Okay. So theta A equals to theta B equals to theta C, which is equals to theta max. Why? Because the cross section is the free end, so maximum angle of twist is at the free end of the cross section. Okay. So how can I find out the value of this theta? Tau by R equals to T by J. Okay.
TL by G.
Yeah, equals to G theta by L. So if I write this tau is equals to G into R theta by L. And what is this R theta by L? Is nothing but phi.
Yes, sir.
Yeah. So I have to write theta max equals to phi into L divided by R. Okay, so phi I should take it corresponding to this capital R. So it should be 1.25 into 10 to the power of minus 3 into length 1 meter divided by R. R is 0.05. So the final answer would be 0.025 radians. Okay? Understood
Yes, sir.
now? Yeah.
Sir, once
Yeah. Again I have to repeat it?
that value substituting part.
Okay. Can I proceed to the next step?
Okay, sir.
Yeah. So angle of twist at a cross section located at a distance of 0.4 from the free end. Okay. So we have already seen theta is directly proportional to length of the shaft. Okay. So they want 0.4 meter from the free end means how much meters from the fixed end? 0.6, right?
Yes, sir.
Yeah. So theta is directly proportional to L, where L is the length of the cross section from the fixed end. Okay. So I know the theta at the free end. So theta dash divided by theta equals to L divided by capital L. So I want theta dash corresponding to length of 0.6 meters. So it will be theta 0.025 into 0.6 divided by 1. So it should be 0.015 radians. Okay. So from this we have done a lot of objective problems. Okay. And in the next class we will see about shaft in series, shaft in parallel, and then statically indeterminate shaft. Are there any doubts?
Sir, please show this question once.
Yeah.
Okay, sir.
Okay. So I am stopping the class today. So in the next class, I will take torsion of shafts and then thin cylinders, piers, and columns. Okay.
Okay, sir.
Yeah.
Thank you.
Thank you.